The purpose of this fourth and last video is to go through an example which is not sine or cosine. Part of what was weird about sine and cosine are the zero terms, and the derivatives, well, you just see the same functions just repeat after four derivatives. So I wanted to give one last example of something else and also just wrap up some of the ideas. You may, by the end of this, the main content of this video, you'll have seen a lot of techniques, but I kind of want to wrap up and compare and contrast some things that are going on as well. So I'll take the function now, natural logarithm of x, use 2 as a center, and so, well, we can just compute, well, the zeroth derivative is the original function. Here's the first derivative, and I'm being very intentional about how I'm going to write the second derivative and further. So I'm being very careful to write something like this. So you'll notice that I've even left a space so that it's kind of easy to see the minus signs. Every other term, every other function, excuse me, here is negative. You see 1 and 2 times 1 and 3 times 2 times 1, 4 times 3 times 2 times 1. You see this exponent, I want to say increase, but the right word is decrease, by 1 each time. And if you actually stare at this and do a little bit of pattern recognition, well, you get something like this. Okay, so the zeroth function, the original function, is left out of the pattern, but everything else fits the pattern. So you have 0 factorial, which is just 1. You have 1 factorial, you have 2 factorial, you have 3 factorial. Okay, all that works for the factorials, and I just copied the minus signs where they are, and you see this is every other. And then otherwise, just the power of x here, you see that as well. Now there's another quick way to summarize this, and it looks like this. So if you talk about, so what's the ith derivative? Well, if I is 0, that's this lonely function by itself. That's ln of x, fine. But then if I is not 0, so everything else fits a nice pattern, and it goes like this. You have -1 not to the ith power. That didn't quite seem to work. I just tried -1 to the ith first, but then realized, well, when I is 1, then if you just had an I there, you'd have a negative, but we actually want a positive in that case right here. So that's why there's an I plus 1. You could also use I minus 1, doesn't matter which. And then, well, there's 0 factorial, 1 factorial, 2 factorial, and look, the 5 factorial matches up with the 6th derivative. This number here is I, so there's I, right? If I is 6, you want 5 factorial. That's why instead of I factorial, you see I minus 1 factorial. Just to repeat, I here is 6, you need 5 factorial, and so this is 6 minus 1, or 5 factorial. Finally, you have x to the negative I, and now, other than the exponent being negative, the number here does match the derivative number. Okay, so this really is the formula. If you're unconvinced, just try it. Take this, plug in I is 0, and you're looking at that formula. Plug in I is 1, 2, 3, 4, 5, and so on into this, and you will see these functions right here. Let's take this and put this on the next slide. I rewrote this just a little. So if I go back to the previous slide, all I did was I took the x to the negative I and put that in the denominator. And why not? I mean, we're done with sort of the format for pattern recognition. And now the point is we're using a equals 2 as a center. That means plug in for the x. That's here, here, and here. Plug in a 2, and that's all that happened here. So this x became a 2, that x became a 2, this x becomes a 2, and that's it. Now the formula for c sub I is take this thing, right? Take the ith derivative at a, in this case 2. So take these numbers and divide by I factorial. So because this is split into parts based on whether I is 0 or not, same thing, this will be split into parts. So all we do here is just take this formula, and in this first sporadic case, divide by 0 factorial. In the other case right here, take this, and you actually see these fractions look very similar. The only difference is, well, we divided by I factorial. This I factorial in the denominator ends up right there, and that's why these denominators are a little different. Just to clean up the algebra here a little bit, so this dividing by 0 factorial, that's just dividing by 1, so this formula is just ln of 2 again, coincidentally the same thing. But otherwise over here, you have I minus 1 factorial and I factorial, and those, you create a lot of cancellation, and all that's left is just an I in the denominator. So get rid of all the factorials, and you just have an I for that. So there's still this 2 to the I in the denominator. So this is a nice clean formula for c sub I, as long as I is not 0. So let's take this formula, ln2, and this formula for I bigger than 0, and put that on the next slide right here. And we don't need to do this, but I thought it might be helpful to actually plug in and see what's going on. So C0, that's this. C sub 1, C sub anything other than C sub 0, we're going to use this bottom formula. And if you plug in I is 1, 2, 3, 4, and so on, you should get numbers that look like this if there are no typos. And you can now take these numbers, all of these numbers here, and go back to the very first video. There was a description of how you find the Taylor series. So C0, then C1 times x minus a to the 1, plus C2 times x minus a to the second, plus C3 times x minus a to the third, plus C4 times x minus a to the fourth, and so on and so forth. So we'll take this, put that on the next slide. Here it is. So here's the Taylor series in longhand format. Notice this one term is weird, does not look like the rest of them. And I just want to also recall the formula for C sub I that we saw earlier. So instead of writing the Taylor series in this longhand format, here's the short version, right? This is the general form. I mean, this is the formula that was presented earlier, just a is 2. But you could rewrite this series, so I starts at 0, goes to infinity, as start at 0, stop at 0, and then start up again at the next number, in this case 1, and go up to infinity. So not a lot is going on here other than this series has been split into 2 separate series. And this series is really boring because this is just one term. It's the term when I is 0. And when I is in fact 0, this simplifies to the 0th power, so that's just a 1, but you just get C sub 0. That's right there. The purpose of splitting like this is that we split, here this deals with I is 0, that's this case, and then here you have I starts at 1 and goes on up to infinity. This C sub I formula then is always consistently the second thing. So we can now, after this simplification in this step, replace the C sub 0 with ln2, and then here, since you're only dealing with I equals 1 and up to infinity, you're never dealing with C sub 0. I is 1, or I is 2, or I is 3. Then you can replace the C sub I with this second formula right there. So this, and there's no other way to take this ln2 and put this into the series, but this is really the shorthand format for the Taylor series of ln of x centered at the number 2, centered at the x value of 2. If we go back and take this, or rather even this, if you write out just this term, or just this term and the next term, or this one, and that term, you have partial sums, and these are the Taylor polynomials. So maybe it'll help if you go back. I'll go back. If you write this down first for a second, pause the video to write this down. Then if you go here, this is T sub 0, it's just the constant. T sub 1 is Taylor polynomial of order 1 or degree 1 that only goes up to the x to the first power. Here's the next term, and here's the next term, and here's the next term. So this is T sub 4. And of course this continues, but I didn't write T sub 5, and so on. We're done with what I would like to talk about regarding a bunch of techniques. Now, you've learned so many techniques in these videos, but I want to summarize one of the key points. What does term-by-term integration do? And the key point I want to make is actually term-by-term integration was used in 2 different ways in these videos. So in the first video, we did this. We knew an antiderivative of 1 over 1 plus x squared. That's arctangent of x. And so what we did was we found a power series representation of 1 over 1 minus negative x squared using geometric series, and we integrated that thing term by term in order to get a power series representation of arctangent of x. And notice what happened here. The key point is that this function, 1 over 1 plus x squared, we know how to take the integral of anyway. This is arctangent of x plus c. Okay, so if you know both a function, its power series, and its antiderivative, well, then by term integration, you get a power series for the antiderivative. And that's great. But more importantly, and maybe much more surprisingly, here's the key point, is that even when we don't know how to anti-differentiate, so here it's written maybe a bit more technically, but sine of x squared, there's no nice formula, no closed formula. None of your integration techniques like U substitution or trig substitution or partial fractions, nothing's going to help you take integral of sine of x squared. But we could still do this integral sine of x squared dx from x is 0 to 7 using power series. And this was an outline of what we did. We started with a power series representation of sine of x, and here we did take derivatives of sine of x. We took an infinite number of derivatives and found what c sub 0 is, c sub 1 is, and so on. And then, using the power series representation of sine of x, we found the power series representation of sine of x squared by doing a substitution. Take that new power series that you got, and we did a term-by-term integration of this power series, which would give an antiderivative for sine of x squared, but not a nice closed simple formula, rather a formula which is a power series again. And again, that power series was the thing you integrated was a power series, which is basically like a polynomial of degree infinity. And after the integration, one term at a time, you still get something that looks like a polynomial, but is just a different power series. And then with the power series that you have, that antiderivative, we use fundamental theorem of calculus 2, plug in x to 7, and then plug in into the power series again, into the antiderivative power series, also plug in x to 0. And while, yes, you wrote something which has an infinite number of terms, at least that is an expression which gives you this antiderivative. And if you want to compute that number for all practical purposes, maybe you can't take all infinite number of terms, but we saw due to the remainder estimation theorem, due to that great inequality, that even if you take just a handful of terms, you're getting really good approximations of this integral. That's it for all the videos.